All right, welcome to this. We have been talking about interaction metrics that quantify the interaction in a multi-variable system. Interaction metrics. And last time we described what is known as the Linsky index, and by definition, if I have a steady state open loop equation y is equal to k times u, where k is the gain, then the Linsky index is defined as Linsky index is equal to determinant of k divided by product of the diagonal terms of the gain matrix k I. And what we said was that if the Linsky index is less than 0, closed loop system is guaranteed integral unstable. So, this is actually a tool for discarding input output pairings that would be unstable because of unfavorable interaction. And we also said that for Linsky index close to 1, this is at least for a 2 by 2 system, it means that the interaction, the steady state interaction is one way. Okay. So, Linsky index close to 1 in some sense shows that the interaction is not as bad. Okay. All right. Now, traditionally we also have another interaction metric, and that is called the relative gain, or rather the relative gain array. Relative gain array. How do you define the relative gain? Relative gain lambda ij, where I refers to output subscript, j refers to input subscript, is by definition dou yi dou uj, all other inputs are constant, divided by dou yi by dou uj, all other outputs other than yi are held constant. Okay. If you to understand it in plain English, I mean, what you are saying is, if I look at the ij pair, I refers to output, j refers to input. If I look at the ij pairing, then what I have is the definition of relative gain is what is the gain that this pairing sees with all other loops open. All other loops open, what that means is all other inputs are held constant. All other inputs are held constant, divided by what is the gain of this ijth pair with all other loops closed. Now, because all other loops are closed, what we have is all the other outputs other than yi are at their set points. All right. So, the relative gain is the ratio of the gain for the ij pair with all other loops open divided and all other loops closed. Okay. So, this is the English interpretation of relative gain. Lambda ij is close to 1. What that means is whether the other loops are closed or not, the ijth pair gain for lambda ij close to 1, k ij does not or depends very little, does not depend on whether the other loops are closed or not, on whether the other loops are closed or not. The gain that I see k ij is in some sense independent of what is the state of the other loops, whether they are closed or not. So, relative gains close to 1 imply, let us just call it favorable interaction. It does not imply no interaction, but that the interaction is relatively mild and therefore, we call it favorable interaction. Okay. Now, if I, this is my row index and let this be my column index. Okay. I can fill up lambda 1 1, lambda 1 2, lambda 1 n, okay, and so on so forth. Somewhere there will be a lambda ij and then I will have lambda n 1, lambda n 2, lambda. This is called where I have calculated the relative gains of all possible input output pairings. I pair I with j, I can take so many values, j can take so many values. For each of those, when I calculate my relative gain and put it in terms of an array, that is called a relative gain array. Okay. How do I calculate the relative gain array? Well, if you look at lambda ij is equal to dou yi dou uj at where all the other u's are held constant divided by dou yi by dou uj where all the other outputs are held constant, which is the same as dou yi by dou uj uk times dou uj over dou yi, all other outputs are held at their set points. Okay. Now, this is the open loop gain k ij, where my open loop steady state equation is y is equal to k times u. Okay. What is this guy? How do I get this guy? Well, to get this guy, let me invert it and get u is equal to k inverse y. All right. Now, if all the y's are held constant, all the y's except yi are held constant, what that means is that all the terms in this guy except the ith term are 0. Okay. And when I do that, what I will get is u will be equal to k inverse 0 0, the ith element is 1, the other elements are all 0. Okay. And therefore, what I will get is the jth element, because I must look at the change in the jth element, uj will be equal to k inverse j comma I. All right. The matrix, the j ith element of the k inverse matrix will correspond to uj. All right. So, what I get from this is that lambda ij is equal to k inverse this matrix, its j ith element times the gain matrix times its I jth element, and if I have to do it for all values of I and j, then what I get is my relative gain array RGA is equal to k inverse. Now, because the index is not ij, it is ji, therefore, I have to take a transpose Hadamard product. How do I define Hadamard product? Times k, the gain matrix. Let us see, this is element by element multiplication, not matrix multiplication, but element by element multiplication. Okay. So, this is how you calculate your relative gain array, and once you have calculated your relative gain array, you want to find out what is to be paired with what. You look for terms that are close to 1 and then sort of say that the recommended pairing is, let us say I look at a 3 by 3 relative gain array and I find that of all the elements 1 2 3 1 2 3 1 2 3. So, this is I and this is j. What I find is that this element and this element are close to 1. Okay. Then what we say is you should be pairing, this is what 2, output 2, this is y, with input 1, output 1 with input 2, output 3 with input 3. This is the recommended pairing from the relative gain array. Okay. How do you calculate the relative gain array? I just told you, calculate the inverse of the gain matrix, take its transpose and do element by element multiplication with the gain matrix. That is a relative gain array. What should you avoid? Avoid pairings with negative relative gain. Why is that? Well, a negative relative gain is saying that all other loops open, all. See, if I look at the plain English definition of relative gain, it is the gain between the ijth pairing with all other loops open divided by the gain for the ijth pairing with all other loops closed. Now, if this number is negative, what that means is my controller is seeing, well, what that means, let me give you an example. If you increase steam, you would expect that the temperature on the tray of a distillation column should increase. So, gain should be positive, open loop gain you expect to be positive, but for some reason if the relative gain is negative, what that means is depending on whether all loops are open or not. So, if all loops are closed, if all loops are open, If you increase steam, tray temperature increases. On the other hand, if all other loops are closed, what you get is if you are increasing steam, the tray temperature is decreasing. That is what would cause the relative gain to be, when you take the ratio, you will get a net negative number, right. So, that is what would cause the relative gain to be negative, and what this means is that the process gain sign changes depending on whether the other loops are on or not. Okay. So, a direct acting controller must become a reverse acting controller, and a reverse acting controller must become a direct acting controller depending on the status of the other loops. And operators keep taking loops on or off, they will always, sometimes the operator would like to intervene, he will switch off a loop and take control action himself. But if the other loop, the gain sign has changed, that loop would go unstable. Unstable in the sense, instead of increasing the steam, you would keep on decreasing the steam, and the steam valve will ultimately shut down, or vice versa. Okay. So, this is something that is not desirable, must be avoided. So, as a tool for rejecting IO pairings, if you look at the relative gain array, all IO pairings that have negative relative gain should not be implemented. Okay. What should be implemented? What are possible candidates for implementation are all elements with all possible IO pairings with positive relative gains, preferably as close as possible to 1. Okay. While we have practical use, in practice, when you are supposed to figure out what input output pairing should be implemented, practical use would always be common sense. Get the input output pairing from common sense. Once you have that input output pairing from engineering common sense, and what constitutes engineering common sense would constitute the rest of the course. But once you have that input output pairing, check neither Linsky index, check relative gain, alright, and if these are okay, you are alright. So, these are actually in some sense confirmatory tools, tools that confirm your engineering judgment, that yes, this is what I wanted to do, this is what is the most sensible thing to do based on engineering common sense, and look here, the Nether-Linsky index and the relative gain seem to be suggesting the same. So, these are essentially tools to confirm conventional wisdom. Okay. That is my take on it. I do not think these tools have to be used. It would be, let me put it the other way, it would be disastrous to not do this and recommend an input output pairing based purely on relative gain array, because that in my opinion would lead to is something that should not be done. You use your engineering judgment and then use these metrics, Nether-Linsky index and relative gain, to confirm that what you are doing is okay. Okay, and what you would find is 9 out of 10 times the common sense approach actually works quite well. Okay. Just to give you an example, for example, if you take a distillation column, here is a distillation column, a simple distillation column, and do not worry if you do not understand some of the things, this is just an example. Reflux drum, you put in some reflux back into the column, take out some distillate, there is some reboil, you are putting in steam here, that causes the vapor to boil up, and then you are taking out the bottoms. Okay. Let us just say this is under flow control, the feed is under flow control. Well, you have got to control 2 levels, liquid level at the top, liquid level at the bottom. Let us say you are doing it this way. This is probably the most common arrangement. You would also have to control the vapor pressure, the pressure of the vapor that is entrapped in the column, and that the most common arrangement to do that is this. you adjust the condenser duty or the cooling rate in the condenser to control the pressure, temperature control, and let us say you are adjusting the reflux to maintain a rectifying tray temperature. Now, the choice of these two tray temperatures, what you would find is, if I am controlling a rectifying tray temperature using T rectifying is controlled using reflux, and T stripping, some tray temperature in the stripping section is controlled using Q reboiler, the reboiler duty. Okay. If I am doing this, what you would find is typically my neither Linsky index and my relative gains would be positive, possibly close to 1, but certainly neither Linsky index will not be negative. On the other hand, if you do this kind of a pairing, where you are controlling a rectifying tray temperature using reboiler duty and a stripping tray temperature using reflux, now that does not make sense, right. Then what you would find is that these metrics are not well behaved. You may get a negative neither Linsky index or you may get a relative gain that is negative, and therefore, these pairings are not recommended. Now, if you ask an operator, for him controlling reflux, controlling a rectifying tray temperature, the most obvious handle is reflux, controlling a stripping tray temperature, the most obvious handle is reboiler duty. These metrics, neither Linsky index and relative gain, would confirm that indeed that is the way to do it. And they would also suggest, hopefully, that if you do it the other way, well, that is not the way to do it, because you get a negative relative gain and or a negative neither Linsky index. So, these are, I would recommend these as tools to confirm your engineering wisdom, and what the effort should be is to do as much as possible to gather or to become wise in the engineering common sense way. Okay. There is another thing that needs to be discussed here, and that is called decoupling. I would call it dynamic decoupling, and I think this will be the last thing that we do, maybe one more. Dynamic decoupling. See, if I have a multivariable 2x2 system, it is most easily illustrated on a 2x2 system. 1, 2, 3, 4, and what I have is y1, y2, and this is u1, this is u2. Notice, if I make a change here, let us say this goes up as a step. Okay. If u1 is increased as a step, then y1 would give a response, let us say it gives this kind of a response, y2 would also give a response, and let us just say it gives a response. Now, I know I am changing u1, and therefore, I know y2 is going to show a response. What I would like is, how should I adjust u2? How should I adjust u2 so that this signal is the negative of this signal, all right. Then what I would get is y2 does not show any response or very little response, right. So, because I know I am changing u1, therefore, I know y2 is going to change. Can I change u2 in such a way such that the overall effects get cancelled and y2 does not show any response? That is the question I am asking, and I can ask the same question when I am making a step change to u2. How should I change u1 such that this plus this goes to 0? So, then what I will have is, I change u1, y1 responds, y2 shows no response. I change u2, y2 responds, y1 shows no response. This is what is called a decoupled system. y1 and y2 are not coupled with u1 and u2. u1 affects y1, does not affect y2, u2 affects y2, does not affect y1. That is a decoupled system. So, how do we accomplish this decoupling? I can use the philosophy of feedback control. Let me call this u1 star and let me call this u2 star, and you can, since I have drawn that circle, you can think I will be putting in a signal there. What I do is I take this guy, multiply it by some transfer function and add it up here. Now, what should go in here? That is the question. Okay. Well, what should go in here should be such that this and this are negative of each other. So, if u1 is going up as a step, y2 will go to g21. What I would like is that this signal should be minus g21. For this signal to be minus g21, this signal should be minus g21 by g22. Well, so that is what goes in here. What should go in here? Minus g21 by g22. Similarly, if I give a step here, I would like that only this changes, this does not change, y1 does not change. In order to do that, I take this signal, pass it through a transfer function box, and what should go in here? That is the question. Well, what should go in here should be such that this signal is the negative of this signal. Okay. If this is going up as a step, this signal will be g12 times u2. So, this signal has to be negative of that. In order for this signal to be negative of that, what should this be? This should be minus g12 by g11. Well, that is what goes in here, minus g12 by g11. Now, if you look at the input output relation in this box, okay, if you look at the input output behavior between u1 star and y1 and between u2 star and y2, if I go to the next page, there will be trouble. Let us just see if I can fit it in here. Okay. So, let us just see how what is the dependence of y1 on u1 star and u2 star. If I look at, so y1 would be equal to g11 times u1 star, that is this guy. When I make a change here, this decoupler will cause a change in u2, and this change in u2 will give me an additional signal here. Okay. What is that additional signal? That would be plus minus g21 by g22, that is this guy, times g12 into u1 star. So, that is the dependence of y1 on u1 star. What is the dependence of y1 on u2 star? Well, if u2 star goes up as a step, the effect on y1 would be plus g12 into u2 star. Now, because u2 has gone up as a step, this decoupler will cause, what I am saying is this decoupler will cause u1 to move, and what is that movement in u1 would be minus g12 over g11 times g12 this signal is minus G12 over G11 multiplied by G11 times U2 star. Now, if this thing is physically realizable, what I mean is if this thing is physically realizable, then these two terms actually cancel out, right, and what I have is y1 depends only on u1 star, no dependence on u2 star. Similarly, what I will find is that y2 depends only on u2 star, no dependence on u1 star, all right. So, this is called dynamic decoupling, and I have covered it just for the heck of covering it, because it is covered, usually covered most of the places. The thing that I wanted to tell you was that in chemical processes, set point tracking is required only when you are starting up the plant or shutting down the plant. That happens, let us say, once in 2 years or once in a year, set point tracking. Okay. What you are interested in is load rejection. Most of the time, load rejection is kind of like autopilot, okay, in flying. And just to make that point, let us just consider this a single input single output system, GP. I have got a controller. Let us see, something is coming here, and what I have here is GD, and this is disturbance D, this is Y, and what I have is Y set point plus minus, that is negative feedback, this is the error, and this is the input to the process. Okay. So, the disturbance D affects Y through the transfer function GD, okay. And if I look at the closed loop, I mean the overall transfer function, what I will find is if D is 0, how does Y set point affect, a change in Y set point affect Y? We saw that Y, okay, let us just do this, Y is equal to this signal plus this signal, that is equal to, so this signal is GP times U or GP GCE. So, this is actually GP GC error, and the error is Y set point minus Y, and okay, and this signal is plus GD times D. Now, if I take the Y terms on the left hand side, what I get is 1 plus GPGC times Y is equal to GPGC times Y set point plus GD times D, and then if I divide by what is here, what I will get is this is what I get, all right. So, how does Y depend on a change in Y set point or on a change in the disturbance? D, well, this is the equation that governs that shows that dependence. Okay. This is called the servo transfer function that we have seen. This is called the servo transfer function, and this is called the regulator transfer function. All right. So, we were talking about the servo and regulator transfer function. So, if we have a single input single output system with a block diagram as shown here, the dependence of the output on a change in the disturbance and or a change in the set point is given by this equation, and this transfer function is called the servo transfer function, and this transfer function is called the regulator transfer function. And the servo transfer function shows how the output responds to a change in the set point. A regulator transfer function characterizes how the output changes to a change in the disturbance. Now, notice that in both the transfer functions 1 plus GPGC occurs in the denominator, and this is what actually determines the stability of the closed loop system. Why am I talking about the servo and the regulator transfer function? That is because when I am running a plant, I am actually more interested in ensuring that disturbances are rejected effectively. So, I am interested more in the regulator response. My interest in the servo servo response is not as much, because primary objective in chemical processes, load disturbance, effective load disturbance is the primary function of the control system in chemical processes. And what do I mean by that? What I mean by that is, what would constitute a load disturbance? For example, the quality of the feed to the process changes. The quality of the feed to a distillation column changes, the quality of the feed going into a process changes. That is a disturbance into your process. My control system should be able to handle it. Another example, I would like to increase the throughput or change the throughput or change the production rate in the process. So, my heating rate, cooling rate, flow rates, etc. must follow that change in throughput. Okay, must effectively execute that change in throughput for me. So, that is again a load disturbance, more heating load, less heating load. Okay. So, these are throughput changes. Examples of load disturbances is throughput changes, or throughput or feed rate changes, more generally referred to as throughput changes. Another example is feed quality changes. What are other load disturbances? Well, ambient conditions disturbances, we have talked about this. Days are hotter than nights, winters are colder than summers, the cooling water in rainy season is not as cold because cooling towers are not as efficient because the air is humid, and so on and so forth. Okay, so, these are all disturbances. I want to operate at a set point regardless of these disturbances, and that is governed by the regulator response. Okay. Load disturbance is the primary function, set point remains the same. I would like to operate my reactor at this reaction temperature regardless of what is the composition of the feed, regardless of what is the flow rate that is going into the reactor, right. So, that is actually governed by regulator response. So, the regulator response is what is of interest in operating a chemical process around its design steady state. Okay. That is point number 1. Where is set point tracking important? Well, aerospace systems, for example, their set point tracking is important because the missile has to follow a certain trajectory. That trajectory is the set point, the position set point that your missile should track. Similarly, aeroplanes, choppers, etc., robotic arms. So, in mechanical or aerospace systems, set point tracking is important. In chemical systems, it is load rejection or load disturbance rejection, effective rejection or effective handling of load disturbances is what is important. This point I would like you to keep in your mind, because for example, we covered decoupling. Why is decoupling important? Well, decoupling is important because if your objective is to track the set point and you have a decoupled system, what happens in a decoupled system is, if you change input u, only y1 gets affected, y2 does not get affected. If you change input u2, y2 gets affected, y1 does not get affected. So, therefore, the loop for y1 and the loop for y2 can be tuned real tight, and this loop does not disturb that loop and that loop does not disturb this loop. So, where the set point tracking is important? decoupling is useful. Load disturbance rejection, for load disturbance rejection, decoupling may or may not be useful. That is because the transfer function itself is different. And in a papers way back in the early 70s, 1971 probably, Linsky actually showed in a paper that if you implement a decoupler, your load rejection actually becomes worse. Your regulator response with the decoupler in there actually becomes worse. Set point tracking is better off, but there are cases where load rejection actually suffers with the decoupler in there. Okay. So, implementation of a decoupler may or may not be recommended all the while. In fact, if you look at what Bill Lieben has to say, he says we actually do not need decoupling. Okay. But nevertheless, for the sake of completion, I have covered it. Next time what we are going to do is cover probably the last thing that needs to be covered, which is model predictive control. Right now what we have seen is, you got controllers and we have looked at the PID control algorithm, we have looked at how to tune the tuning constants in a PID controller. These PID controllers, for example, may not work very well for systems with difficult dynamics. What is an example of a system with difficult dynamics? For example, systems with a long dead time, or a system with an inverse response, which is also sometimes referred to as wrong way behavior. So, what happens if you got a long dead time? The process has got a long dead time. What happens there is, I have got my process and I have put in my PI controller, y set point y plus minus. Okay, I have put in my PI controller. I make a change here, nothing happens here for a long time. Now, because nothing is happening to the output, the error remains unchanged. The integrator in the PI controller keeps on adjusting this guy. Okay. And what that essentially does is, you cannot have your gain too large, gain cannot be increased. If you try to increase gain to get tight control of y, what you will start getting is sustained oscillation. Okay. So, for large dead time processes, the ultimate gain is small, it is reduced because of the large dead time, and therefore, you cannot, your Kc, the gain that you implement in the controller also is reduced, and therefore, the closed loop response is not as fast and snappy as you would like it to be. Should that be the case, you would like to incorporate a model that tells the controller do nothing, because the process is of that type. You do something, you have to wait, because nothing is going to happen to the output, because there is so much dead time in the process. How do you do that? How do you incorporate a model to accomplish that? Similarly, in an inverse response, what happens is, you do something here, suppose you are increasing the steam here, you expect the temperature to go up, right, but what happens is the temperature actually starts to go down before it can come up. Now, because of this wrong way behavior, again this is worse than dead time. In the dead time, nothing was happening to the output, here the output is moving in the wrong direction. Again, this would cause the ultimate gain to be reduced, this inverse response behavior, and therefore, the gain that you can implement in your PI controller would be smaller, and with that small gain you may or may not, and in the case where you do not get a fast and snappy acceptable closed loop response, you will have to look into model based control techniques. Okay. These model based control techniques is what we are going to come and look at next time, and what I am going to cover next time is, let us see, the Smith predictor, which is for a CISO system, and then dynamic matrix control, and that I believe would put an end to whatever control theory is to be told or is to be covered in the 9 or 10 lectures that it was supposed to be covered in. Thank you.